Hi there. In this video I'll be talking about heat. We'll be learning about how to use the two heat equations, one of which relates to a material's change in temperature and the other which relates to its change of state. Here's a question from the National 5 specimen paper. A fridge freezer has water and ice dispensers as shown. Water of mass 0.100 kilograms flows into the freezer at 15 degrees Celsius and is cooled to 0 degrees Celsius. We're then asked to show that 6.27 times 10 to the power of 3 joules of energy is removed when the water cools. Since this is a question which relates to a change in temperature, we're using this equation. C is the material's specific heat capacity, which is found in the data sheets at the front of the exam. M is its mass in kilograms, and delta T is the change in temperature. Now, whether the material's heating up or cooling down, delta T is always calculated by subtracting the lower temperature from the higher temperature. In other words, delta T is always positive. Substituting our values into the equation, we get this, which works out to be 6,270 joules, which is of course equivalent to 6.27 times 10 to the power of 3 joules. It's important to note that this is a show question. When you're asked to show something in the exam, all steps in the calculation, including the stated answer, must be shown. Part B of the question asks us to calculate the energy released when 0.100 kilograms of water at 0 degrees Celsius changes to 0.100 kilograms of ice at 0 degrees Celsius. We're obviously using a different equation here because there's no change in temperature, just a change in state from liquid to solid. The equation to use is this one, where M is the mass in kilograms again. L can be found in the datasheet at the front of the exam. The only problem is that each material has two values of L. When we're dealing with a change of state from liquid to gas, or vice versa, then L is the specific latent heat of vaporization. If, however, the material is changing from a liquid to a solid, or a solid to liquid, then L is the specific latent heat of fusion. For this question then, we need to find the specific latent heat of fusion of water. Substituting into our equation, we get 0.100 times 3.34 times 10 to the power of 5, which is 3.34 times 10 to the power of 4 joules. If you'd like to know a little more about specific heat capacity and specific latent heat of vaporization and fusion, then watch my definitions video on properties of matter. On to part C of the question. The fridge freezer system removes heat energy at a rate of 115 joules per second. Calculate the minimum time taken to produce 0.100 kilograms of ice from 0.100 kilograms of water at 15 degrees Celsius. So, first of all, the total heat energy removed from the water is the 6.27 times 10 to the power of 3 joules it takes to cool it from 15 degrees Celsius to 0 degrees Celsius. This was the answer from part A of the question. Plus the 3.34 times 10 to the power of 4 joules to change it from water to ice. The answer from part B of the question. The total heat energy removed then is 3.967 times 10 to the power of 4 joules. The final part of the question isn't too tricky, as long as you realise that 115 joules per second is equivalent to 115 watts. In other words, this is the power of the fridge freezer system. That means we're using this equation to find time, but rearranging it to make time t the subject, like so. Substituting our values of energy and power, we get a final answer of 345 seconds to 3 significant figures. The reason why this is stated as a minimum time is discussed in the next part of the question. Here it is. C part 2 asks us to explain why the actual time taken to make the ice will be longer than the time calculated in part C1. I've seen so many pupils answer questions like this wrongly. They just answer automatically that heat energy is lost to the surrounding air. Well, that's not the answer here. If we had a nice cup of tea, then since its temperature is greater than the surrounding air, it would lose or transfer heat energy to the surrounding air. This explains why a kettle would take longer than the calculated time to boil a certain mass of water. This question, though, relates to the time taken to produce a certain mass of ice as the fridge freezer system removes heat energy from it. Why this takes longer than the calculated time in C part 1 is because the heat energy is absorbed from the surrounding air, which is at a higher temperature. This means that more heat energy will have to be removed. And that's our answer. Heat energy will be absorbed or taken in from the surrounding air, so additional heat energy will have to be removed. And now, I'm sad to say, that's the end of our video. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening.